Welcome in everyone. Hopefully, all the sessions have been amazing so far. And without further ado, I welcome me to give a warm virtual welcome to Claudio.
Thank you, Patricia. So my name is Claudio, and I'm a machine learning engineer at Molly. For those of you who doesn't know, Molly is a payment service provider operating in Europe. And today I'm going to present to you how to effectively use embeddings in tree-based model. So let's first take a look at our problem definition. This is a problem that is relevant for us if we have a machine learning model that has a multi-model input variables, and we decide to solve this problem using a tree-based model. An example of such problem is house pricing estimation. I think this is a kind of a pretty crucial case study for us because in house pricing you have structured data that are really relevant to your problem. For example, square meters, number of bedrooms of postcodes are usually very strong predictors of selling price. And already just by leveraging your structured data, you can already provide an accurate forecast of the selling price of a house. However, sometimes we also have other information available about the house we are trying to predict. We have information about, we have the photos of the house, and we have, for example, the house description. And these are information that we could also include in our model in order to increase our prediction even further. So in those cases, when we have different types of input variables, in this case, structured tabular data and unstructured data, images and text, we talk about multimodal input. That's the meaning of a multimodal input. So how can we approach this problem? Of course, a tree-based model cannot take unstructured data out of the box. We need to do something about it. And the first step towards solving this problem would be to transform our unstructured data into structured data by using an embedding model. So what is an embedding model? An embedding model is a model that has been pre-trained on a different task. For example, an image embedding model is often a model that has been pre-trained on image classifications. And since more often than not, these models are neural network based, they keep within its own weights an hidden representation about the image that they're trying to make predictions on. Once the model has been trained, we can reuse this model by extracting the internal informations that the model keeps of that image, and we call that embeddings. Similarly, text embedding models are other models that have been trained on other tasks, like masked language models or sentence similarity or predicting the next token. And in a similar way, we can reuse these models to extract the internal representation they keep of text to embed text, essentially. Embedding models have risen in popularity in recent years, mainly because of the rise of large language models. So what this means is two things. First of all, a lot of companies already have contracts with large language models providers that very often also provide APIs for other types of embeddings, like text embedding also. Some of them also provide image embeddings. And moreover, we already have models that have been pre-trained on text. And yeah, we have a sudden explosion of text embedding models. And some of these models already support multimodal input out of the box. If you think that, for example, nowadays you can go to whatever large language model and say, give it an image and giving some text, and it will be able to answer your question based on your image. Well, that's, of course, a multimodal input. And it is also possible to generate embeddings from multimodal input directly. Well, an embedding vector is something that looks like this on the right side of the slide. And in essence, you can see it as an array of multiple numerical values. Usually these arrays range on the dimension of several hundred of values. And that's going to be essentially a numerical representation of our unstructured data, and it's going to be, of course, structured, because embeddings are always going to be the same size. Right. Once that we obtain our structured version of our unstructured data, we can, one way to solve this problem is to concatenate our embedding vectors with our structured data, because we're concatenating structured data with structured data, obtaining in this way a data set of only structured data, and we can proceed with training our tree-based model as we would usually do, as if we have only structured data. This is definitely one way to solve the problem, and it's, if your unstructured data is relevant for your problem, it is likely to already give you some performance gain. However, I would argue that due to how tree-based models work, including your unstructured data following this pattern is probably not the best way, and there are a more optimal way of doing it. And that's essentially what I'm going to talk you through in this presentation. So when you look at, so let's see, first of all, why the tree-based model don't work really well with embeddings. When you look at the tree-based model, it looks like something like this. So it's essentially a sequence of binary decisions in which you'll see at each step, we only look at one value, at one column, in order to make our split, in order to make our decision. In the context of house pricing, a possible tree might look like something like this. First, it's very likely the model is going to look at the size of the house, and it's going to use this information to separate bigger, higher value houses from smaller, lower value houses. And then it's going to further split those groups by looking at other features, which could be the number of bedrooms or the age of the house, and so on and so forth. What I want you to communicate with this slide is that the number of features that a single tree can use, it's limited to the depth of the tree. Of course, this relationship is not linear, but it is exponential. So of course, the number of features grows exponentially with the depth of the tree. However, depth is always something that we want to often regularize when training tree-based models. We want to do it to reduce the possibilities of overfitting of such models. So we always want to keep the depth of our tree limited. When, on the other hand, we look back at how an embedding vectors looks like, we understand maybe why the two things don't work well together. Well, embeddings have hundreds of dimensions. Each dimension is a numerical value, so it's not Boolean, meaning that we may need to split on the same value multiple times in order to extract all the relevant information from it. And numerical embedding vector are dense, meaning that we need to use multiple dimensions simultaneously in order to extract all the information from it. So what this means is that a decision tree would have to make really a lot of splits on an embedding vector in order to extract information from it, meaning that it would have to grow very, very deep to fully extract information from embedding vectors. Well, decision trees are kind of, tree-based models are kind of the only model that have this problem. There are a lot of other models that don't have the same issues. And what I argue is like what would be the best way to include embeddings in a tree-based model is by leveraging the strong points of non-tree-based models. If you look, for example, I don't know, even a logistic regression or a small neural network or a support vector machine, they are able to integrate embeddings, to look at embeddings all at once, and are able to, for example, associate a weight to each embedding dimensions. They don't suffer from the same problem of that was tree-based models. So with the solution that I would like to suggest to how to include embeddings in tree-based models, it's essentially a stacking ensemble. It's a bit of a specific case of a stacking ensemble. And the way it works is what you see on the slide. You would essentially start from, from the same setup that we had before, in which we convert unstructured data into structured data. We convert them into embedding vectors. And then once you obtain these embedding vectors, instead of sending them directly to the tree-based model, we use the embedding vectors to train a non-tree-based model, for example, linear regression, whatever. And at this point, instead of At this point, what we do is like we use the non-tree based model to make predictions only looking at embedding vectors, and we pass those predictions to our tree-based model. So the advantage of using stacking in this way, instead of passing the embedding vectors directly to the tree-based model, is that in this way, the tree-based model only receives one column, which is the output prediction of our non-tree-based model. And this one column is what represents our unstructured data. So it's going to include information from our unstructured data, and it's going to give it to our tree-based model. Moreover, since our prediction is of course being created also from something very relevant to the target, we are gonna have a variable that is going to be highly correlated with our target, and it's going to be very relevant to our problem. Of course, some of you might look at these slides and may think like, hey, but we are using target to generate features. Doesn't this introduce target leakage? Of course, if we just perform this operation exactly as I explained you in a very simplistic way, then for sure we are going to include target leakage, because essentially we use target to generate features. However, there are techniques that can be used to essentially have target-free features while using target. And one of these technique is called cross-fitting. Cross-fitting is what's used very often in stacking ensembles, and it's also seen in target encoding of categorical features. And in general, whenever you want to use your target variable to generate features, it's a good idea to use cross-fitting. I'm going to have like some graphics in the next slides to explain how it works. So let's see them. Essentially, cross-fitting works in a very similar way as a cross-validation. And like cross-validation, it starts by taking your initial train set and splitting it into different folds. For example purpose, here I'm splitting my train data set in in 5 folds. And once I've done it, I'm going to start from my first fold, in this case, fold number 1, and I'm going to take all the other folds, the remaining 4 folds in this case, and I'm going to use data from the remaining 4 folds to train my non-tree based estimator. Okay, at this point I have this model that I've only seen, for which I've seen the remaining 4 folds, and I'm going to use it to predict using data from the first fold. And this way I'm going to obtain predictions for the first folds. Then I'm going to continue the process by leaving all the other folds out and only using one of the folds, and I'm going to generate predictions for the next fold, and so on and so forth. In this process, I'm going to generate predictions for all of the folds. But this is something that we need to do only when we want to train our model. At the end of the process, when we want to train our final non-tree based estimator, we are going to look at our entire train set, and we are going to create yet another non-tree based estimator, and we are going to store it. And this non-tree based estimator is going to be stored together with the general model, and is going to be used at the prediction time, for example, during inference or whenever you want to test your model, to generate predictions from embeddings on unseen data. So for example, on our test set. Cool. In the next slides, I want to show you how to do essentially what we have seen before using scikit-learn. There is like a very convenient class that scikit-learn gives us to perform cross-fitting essentially, and it's called the stacking regressor. So stacking regressor already has cross-fitting implemented inside, and we can leverage it to train our tree-based model, which in this case I choose a random forest regressor, as well as a linear model, as a non-tree based model. In this case, I've chosen a linear regression model. And together with these imports, I'm also going to take some other imports that are essentially going to tell us to discard or select specific columns. I'm going to use as an example a data set that just made up. It's kind of a house pricing data set in which I'm going to have 2 tabular features, which are the square meters and the number of rooms. It's just going to representing our tabular data. And I also decided to include the 3 embedding dimensions, which are going to kind of simulate embeddings you obtain from, I don't know, description of a picture of a house. And finally, we have our target variable, which is here, which is the price of the house. In here, I'm defining essentially the linear model pipeline. Maybe the code looks complex, but the only thing that I'm doing here is essentially specifying in this line here which column do I want to include into my linear model. And what I'm saying is that I only want embeddings column into my linear model. And here I'm instantiating my linear model in a very similar fashion. Here I'm instantiating my tree-based model, and I'm doing essentially the opposite as I did in the previous step. In here, I'm specifying that I want to select everything except the embeddings, because we're going to use embeddings just on the linear model. And I have to do it in this way, essentially with the index of the column. I cannot use the column name because there is an issue in scikit-learn. Yeah, doesn't matter. But that's how you would do it in our example. And finally, the only thing I'm left to do is to combine those 2 estimators into a stacking regressor, like so. And essentially, I'm just saying, okay, the initial estimator is my linear model. I can also put multiple ones if I want. And my final estimator is going to be my random forest pipeline model. And the most important part is to say pass through equal true. What this argument does is telling stacking regressor to pass all of the input features to our final estimators alongside all of the predictions made by the previous models. So in this way, we are sure that we are going to pass, let's say, the size of the house and the number of rooms alongside the predictions of the linear model to our final model, which is essentially what we want. And as you see, stacking regressor also takes a CV argument, and that's because it's going to perform cross-fit in order to fit these 2 estimators together without introducing leakage. Once we have defined our model ensemble this way, we're just going to proceed with the standard training procedure of scikit-learn. And that's explanation of how you can implement this in scikit-learn using pretty basic tools and classes from scikit-learn. Last, I would like to bring you a real life use case that we had in Molly. And I wanted to show you a bit of the performances that we got when using different techniques to include embeddings into our model. So the problem that we were trying to solve was a web shop classification. So being Molly a payment service provider, our customers are usually web shops that uses our services. And of course, we do a lot of analysis on them, as you can imagine. I cannot be very specific with this use case, unfortunately, but yeah, I think for the sake of explanation, it's going to be enough. For our problem of web shop classification, we have a structured data firmographic information. And as unstructured data, we also had available the web shop text content. So essentially the content, the textual content that you see when you load the page of the web shop. For this use case, we use a performance metric that it was a custom one. I don't want to explain it in this context. It was a bit complex, but you can think as something very similar to a weighted PRAC, so precision recall, under the precision recall curve. And I wanted to show you a bit of the different performances that we obtained when we didn't use any embedding data. So in this case, we only use structured data, just the firmographic information. We obtain a performance of 66%. Then if we just include embeddings directly into the model, so without doing the stacking ensemble thing, but just by concatenating the embeddings with the rest of the structured data, as we see an increase in performances of about 1%. However, when we feed the embeddings transformed via stacking, so in the second way that I explained, we see an improvement an increase in performances, which is 3 times bigger than just passing the embeddings directly. So this kind of, at least for our specific use case, passing embeddings via stacking led a much bigger improvement than just passing the embeddings directly. Of course, your mileage might vary, but given the structure of tree-based model, I see that it's very likely that reducing the dimensionality of your embeddings in some way is going to make the embeddings a bit more digestible for tree-based models. All right, so this was the end of my presentation. I wanted to leave some time for questions. So this is the time. Now I will take your questions, and yeah, we'll be very happy to answer if you might have any. Right? I don't know if was everything clear. Someone wants to still ask something. So let me try to, if I see if I can put it on stage. This is the question. If a tree does recursive partitioning, can not partition the embedding space? Recursive partitioning, cannot partition the embedding space. Yeah. Yeah, of course, like a tree can definitely split the embedding space. Like it's definitely possible. The problem with it is that it will take really a lot of splits to do it. So it's in the slide here a bit. So essentially, a tree can definitely leverage embeddings. However, the problem with trees is that it needs to split multiple times in order to fully leverage the embedding space. Imagine that a tree needs to split on a table which is, I don't know, 700 dimensions. Everything is numerical. At every split, the model is going to split on one of the dimension of the embeddings, meaning that it is going to use a lot of splits to fully use even to make a single split on every dimension. I hope this answers your question, Jonathan. If not, please send another message. Yes. The question, is it possible to get a copy of your slides? Yes, we are gonna, I think you should be able to get the slides under the resources. Yeah, thanks, Ash, for replying. All right. Cool. I think that was it then. If you still have questions, maybe after. All right. There is one more interesting thought. What is your preferred way to embed the non-embed? Okay, let me put it on screen. So the question is, what is your preferred way to embed non-structured features? So I would say like there is not really a preference. It really depends on the input that you get. For example, if you have a mix of input, like for example, you have both images and text. You can embed images using an image embedding model. This will obtain kind of one column, and then you can also embed text using a text model. This is going to obtain kind of two columns, and then you can decide to either put the two columns into kind of to concatenate them in a, let's say, vertically, and to put them into your non-tree based model in this way. Or you can also decide to make two different non-tree based models, kind of stacking, let's say, two non-tree based model and one tree based model in one go. And this is how you would do it, essentially. This is our way of doing it. Or you can also use a multi-model embedding model, where you can pass images and text together in order to get embeddings. And I would say, like, in this one, there's really no free lunch. I would say do what's more convenient for you and also try different things. If you already have a subscription where you can get embeddings as a service, like via API, maybe try with that. It's probably low effort way of generating embedding. Otherwise, you can also download a pre-trained model from Hugging Face and embed things yourself. There's both different possible. All right, let's see if there are other questions. Maybe explore different non-tree based models. So for this specific use case, yes. What we did, essentially, when you start this part here, when you have embedding data and you have non-tree based model, you can essentially try different non-tree based model, and using cross validation you can already assess performances of different non-tree based models, because yeah, here we have kind of your train data, here you have the target variable. You can use cross validation, varying different non-tree based model. You can try different models and ultimately choose the one that has the highest performances. Or you can of course try the entire stacking pipeline, and then maybe you can also do hyperparameter tuning, where the class of your non-tree based model is a hyperparameter. That's also another way of doing it. In our case, we use linear regression, and it was kind of the highest performing. Um, does your model have any relevance in environmental pollution? You mean that, so Albert, is your question more related if the embedding model is going to be kind of more, we're going to have like a higher footprint than like non-using the embedding model? I think this is your question. I would say yes, like usually neural networks are pretty heavy to run. So of course, not using any unstructured data and just relying on the structured data is probably the most, like, you're going to have the least environmental footprint. Yeah, also depends what you're trying to optimize, of course. All right. Any last question?
Awesome. Well, thank you so much, Claudio. It was an amazing talk. And thank you, attendees, for joining us for this session. We can most definitely continue the discussion in Discord. We have about 2 more minutes if you have any other questions. If not, we'll end this session for now. Please note that the session will be have a replay immediately after we end this session. So enjoy the rest of the conference.
Thank you all for joining. Bye. Enjoy the rest of the conference.
Bye.